This presentation is about the design of sequential circuits, and the starting point usually is to show a circuit that acts as a counter, although it may not be counting in the usual counting sequence like 1, 2, and 3. It may be counting in weird ways, but they're called counters. They repeat a certain binary patterns, and we're going to deal with their design today using different kinds of flip-flops. So in such a design, the first step is always a state diagram that specifies the desired operation. So over here, you see a state diagram that shows how we would like this counter to behave. It counts from 000 to 100, 111, 010, and 011. So not really a regular counting sequence. If it starts in a state in the state 001, then from here it will go to 111, and then from there it will just enter this loop, and it will stay forever in this loop. So the bits, zeros and ones, are going to be represented by flip-flops. So this state diagram indicates a system that consists of 3 flip-flops, each one dedicated to 1 bit position. And we would like the flip-flops to change states from 0 to 1 or 1 to 0, orchestrated in an appropriate way so that as a whole the collection of these 3 flip-flops will follow this pattern. That is what we would like to do. Again, remember that the state of the system corresponds to a snapshot of where exactly the system is at any given time. So each one of these circles, called the state, represents a particular pattern of activity of the 3 flip-flops that is collectively referred to as the state of the system. So this is why this diagram is called the state diagram, and it simply shows the desired behavior of the system by specifying how the system should transition among the various states that it can assume. Of course, in order to achieve this transition, each one of the 3 flip-flops in the whole system must do a specific transition depending on the state. For example, if the system is at this state, so flip-flop A is a 0, flip-flop B is 1, and flip-flop 3 is 0. So when the system finds itself in that state, then the next state should be 011, which means that flip-flop A should not transition to anything. It should just remain at state 0. Flip-flop B, the same. It should not change. It should stay at 1 as it was. But flip-flop C must transition from 0 to 1. Then from this state, in order to go to this state, the flip-flop A should not transition, should not change state, but flip-flop B as well as flip-flop C must change their outputs and go from ones to zeros. And of course, all of this has to be orchestrated so that they all, if they must transition, They all are transitioning at the same time, or not, but in a coordinated way. So from here, both of this must transition. This one must not transition. That is a coordinated, um, a coordinated effect. Okay, you go from this state to this state. You see, both of these must transition, and this one must remain the same. That's going to be coordinated again. All of these transitions or non-transitions, they have to be coordinated so that they happen exactly as specified. One other thing to note before we continue is that the transitions, as we explained them, depend on the current state, the state in which the system happens to be at any given time. So if the system is in this state, then this is what we want to happen. So the state diagram is a overall description of how we want the system to behave. To proceed, we're going to simplify the state transition diagram to be just this loop and nothing else for simplicity. We will see later that you can have systems where the state diagram is not just a loop. It can be a very complicated collection of states with all sorts of different transitions going forth and back. But for now, we're going to limit ourselves to a loop, which actually is the reason why systems like these are called counters. So the next step is going to be to translate this state diagram into a state transition table. So in other words, express this same thing but in a tabular form, like this. So this is going to be the state transition table, and it carries the exact same information as the state transition diagram. The way you make this is you put over here the various states, and then over here you put the corresponding next states. So if you go to the transition diagram, you see that if you are in the state 0, 0, 0, the next state is the state 1, 0, 0. And so 0, 0, 0 goes over here, and 1, 0, 0 goes over here as the next state. The state is collectively the states for the flip-flops A, B, and C. And what is shown over here is A plus, B plus, and C plus, which is the next states of these flip-flops, which collectively make up the next state. So as you see, we have over here all the different states that appear on the state diagram, and here we have the next states. But this table has a few more things that are not immediately observable on the state transition diagram, but it is implied. So there is a state over here called 001. Now, as you see, the state 001 does not appear over here. Okay, with 3 bits, you can have 2 to the 3 different states. Therefore, 8 different states altogether. And over here you have 5. So there are 3 combinations of 3-bit codes that do not appear on the state diagram. These represent states that will never be assumed. The system will never find itself in any of those 3 missing states if it is supposed to behave the way we want it, exactly like this state transition diagram. But the state table does contain all of the states. We're going to need them and will be obvious soon. This is a state, this one of those states that will never appear, will never be assumed. And these are the other two. These are states for which we do not care what the output of the flip-flops will be. So they are, in fact, don't cares. These outputs can be designated to be anything you like that suits you or makes your life easier when it comes to optimizing the design. Why? Because they're never going to appear. So if they're never going to appear, you might as well define the next stage to be anything you want, and exactly as it suits the optimization of the design. So the table now is showing how we want the system to behave in more detail. The next step is to produce the controls that will control the flip-flops to actually do these transitions the way we want them. So this table shows how the flip-flops need to transition from state to state, and our next goal is to figure out how to control them in order for them to do these particular transitions. So what we're after is basically three flip-flops, okay, that are going to represent the first, second, and third bit each respectively. So in this case, the flip-flops shown are JK flip-flops, and the Q output of each one represent the A, B, and C. So this might as well be A, this B, and this C. Now, you're going to need a combinational circuit over here that will receive as inputs the current state. So this is the current state. These outputs here represent the current state, the state in which the system is in at this moment. The control circuit right here will receive this as inputs, and what you expect it to do is to produce outputs that will control the flip-flops. In other words, it will produce the J and K controls to each one of the flip-flops in such a way so that when this is a particular state, current state, these controls will make these flip-flops go to the next desired state as per the transition table. So this is what we're after. This is the overall design of the system that we're after. Now, talking about these controls, we have to also review how the various flip-flops do their transitions. And this one is a list that shows all the flip-flops that we normally use and showing their desired transitions and controls. So starting with the RS flip-flop, it has two inputs, R and S. S stands for set, R stands for reset. Normally, this input, when it's the only active input, it will set it. So the output will be 1, as you see over here. If the set is 1 and the reset is 0, then the output is going to be 1. If the set is inactive and the reset is active, then the flip-flop will be reset. It will be 0. If both set and reset are zeros, then the next state is going to be exactly what the previous state was. In other words, the flip-flop is not going to change state. It's going to remain to whatever state it was. And the RS, in the RS flip-flop, the R and S signals can never be active at the same time. And the reason that they cannot be active is because the next state of the flip-flop will be undefined. It will be something. It will be either a 0 or it will be 1. But what it will actually be will depend on which of the two states is going to win the race. But it's something that you cannot count on. That's why we call it undefined. And so we never want to allow both the R and S signals to become active at the same time, which is why the RS flip-flops are not really as much in use. The JK flip-flop, remember that it was a, a variation of the RS flip-flop, and it basically solves the problem of both the S and R inputs being active. In a way, the JK flip-flop is like an RS flip-flop, with the J acting as the set and the K acting as the reset, except that it is possible to have them both active. And the only difference between this flip-flop and the RS flip-flop, they will behave exactly the same, except in this case, when both the J and the K are active, then the flip-flop just flips state. If it was 0, it will become 1, and if it was 1, it will become 0. So in other words, the next state is going to be the complement of the previous state, or the current state. Now, this is the JK flip-flop. The delay flip-flop is a very simple one, and normally it has a clock trigger, and whenever it is triggered, it will simply latch on whatever happens to be at its input, and its output will simply become a copy of the input, and it will remain at that until the next time it is triggered again to do a reading of its input to the output. That is why it's also called a delay, because all it does, it delays the input. It makes a snapshot of the input and holds it until the next trigger that it receives, at which time it will make a new snapshot of the input to the output, of course. The trigger flip-flop, the only thing it does, it simply toggles every time that it gets a trigger. So you see, as long as the only input that it has, the trigger input, is a 0, the next state is going to be whatever it was before, the current state that is. But when it's triggered, then the next state is going to become the complement of the current state. So it's going to toggle. That's why sometimes the trigger flip-flop is also called the toggle flip-flop. So this is how the flip-flops behave. Now, remember this arrangement. We're now going to condense it into a compact form. So we're going to have all of these tables together in one equivalent table. So this is the combination of all of them. So this table here shows the controls that are needed for each desired transition. So over here, we're showing a desired transition. So if this is the current state, and we want this to be the next state, then the table shows what the controls should be for different kinds of flip-flops based on the transition. So as you see, we have here transition 0 to 0. In other words, there is no transition, but we call it that because that's what this table is all about. So if the flip-flop is going to remain at 0, then what should the JK controls be for a JK flip-flop? So the K and the J could be zeros, in which case you're going to have exactly the no activity, and the flip-flop is going to stay where it was. But the K can also be 1. It can be active. And here's why. If as long as the J is 0, the K, if it is active, it will be trying to reset the flip-flop. So it will be trying to make it go to 0. Now it was 0, therefore trying to reset it is not going to have any effect. But it indicates that, you know what, you can have, as long as the J is 0, the K can be 0 or it can be 1. In other words, you do not care what the K is going to be. Now, this is going to be very useful when trying to optimize things, as we're going to see. On a transition from 0 to 1, what do we want to do? We basically want to set it. So J should be 1 in order to set. Now K should be 0. But what would happen if K was 1? If K was 1, according to this table here, 1 and 1, the flip-flop is going to toggle. So if it's going to toggle, then what's going to happen? It's going to go from 0 to 1, which is exactly what we want. So as long as the J is 1, it really doesn't matter again what K is. Because if K is 0, then the J will simply set it. If K is 1, it will toggle, so you're still going to get the exact same effect. Next, transition from 1 to 0. In this transition, it seems that we want to reset the flip-flop. So you really would like to have K be active and J obviously be 0. But if J is active too, then what is going to happen is that the flip-flop is going to toggle according again to this entry of the JK flip-flop table. So for this transition, as long as the K is 1, it does not matter what the J is. If the J is 0, okay, 0 and 1 for the K, that will mean a reset, and you're going to get your transition from 1 to 0. But if the J is 1 and the K is 1, then you're going to have a flip. So since it was 1, it will flip to 0. You still have your transition. Similarly for this transition here, well, there is no transition. It was at 1 and you want it to remain at 1. So if both J and K are zeros, that's fine. Or you could pretend that you are trying to set the flip-flop and turning it to 1. Of course, if it was at 1, trying to set it is not going to have any effect, and it's simply going to remain at the same state 1. So that will do as well. But that means that as long as the K is at 0, the J can be anything you want. So it is a don't care. So that is how the controls work for the JK. If we're looking at the RS, you will notice that for the most part, the RS flip-flop has a similar activation just like the JK, except that it doesn't have as many don't care entries. The reason is that you do not want both the inputs R and S to be both 1. So if you look at this entry, for example, the JK at this particular transition, for this particular transition 1 to 0, it can have both J and K to 1, but the RS flop cannot. Okay, so if this must be 1, this one has got to be a 0. So if the R must be 1, then the set must be a 0. Now, if you remember that the K acts as a reset, then it would follow that the reset over here should be the same as the K, and the set should be the same as the J, except that wherever you have the possibility that you have both inputs being 1, that cannot be allowed. So if this one must be 1, if this K must be 1, then this R, this reset, must be 1. So the set cannot be 1, it has to be a 0. So this is how it works. But anyhow, another way to see this is as follows. Take this transition, for example, 0 to 1. So what do we want the RS flop to do? We want it to go from 0 to 1. So basically we want to set it. Okay, so we want to set it, and in order to set it, according to this activation table, the next state will be set if the set is at 1 and the reset is at 0. So for this transition where you want to set it, the set has to be 1 and the reset has to be 0. Similarly, over here you want to reset it. You're going from 1 to 0. So you're resetting it. So you want the set to be at 0 and the reset to be at 1. When there is no transition, when the state remains the same from 1 to 1 or from 0 to 0, then what you must make sure is that one of the inputs is not triggered. For example, if it was at 0, in order for it to remain at 0, the set must not be activated. Okay? The reset can be anything you want. It can be 0, it can be 1. They're never going to be the same. Like both of them are never going to be 1 in this case. So it is allowed for the reset to be anything you want. In the case of the state being 1 and remaining at 1, what you must make sure is that you do not trigger the reset, because you do not want to reset it. You want to leave it alone. So the reset must be at 0. The set, however, it can be at 0, or it can be active as if we're pretending that we're trying to set the flip-flop. And that explains this entry of this table. The trigger flip-flop. The trigger flip-flop, you're simply looking at where do you have a change of state. That's when you have to have a trigger. So you see in this case, when it's going from 0 to 1 or from 1 to 0, you have triggers for the T flip-flop. And in the other cases where you have no transitions, you have zeros, 0 and 0. The delay flip-flop. The delay flip-flop, basically, you have to feed it the output that you want it to assume. So the D input is always going to be the next state, the next desired state. So you see that over here, it is exactly identical to the next state, because the D control has got to be what the next state needs to be. So if the next state needs to be 0, the D has to be 0. If the next state has to be 1, then the D has to be 1. because that is what the flip-flop is going to latch on. And so for the D flip-flop, very simple, the control has got to be exactly what the next state you wish to be. Now that we know what transitions the flip-flop should make in order to achieve the desired sequence, and that we know what controls we have to provide to each particular flip-flop or flip-flop type in order to make those transitions, we proceed to augment the transition table with the controls. In this particular case, we are using RS flip-flops, so we're going to need an R and S control for the flip-flop A, and similarly for B and C. So we need 6 controls altogether. So these controls are shown in this table, and let's take a few of these entries and try to go over them to explain how they work. So looking at the flip-flop A, in this particular entry, the first row, that shows the transition from state 000 to 100. So the flip-flop A, for that particular transition, it needs to flip from 0 to 1. So its current state is 0. This is the whole current state of the system. And the next state of the flip-flop A needs to be 1. So given that it is an RS flip-flop, what do we need to do? We need to set it. Therefore, the set signal for A is going to be 1, okay, while maintaining the reset at 0. So the transition 0 to 1 for an RS flip-flop is a set. So we're going to set this, and we're going to keep the reset at 0. Looking at flip-flop B. Flip-flop B does not need to transition at all because it was at state 0 and it needs to remain at state 0. Therefore, we need to do nothing. So we're going to maintain the set signal for B at 0 because, of course, we do not want to set it. But for the reset, well, if we keep the reset at 0, it will do nothing, so it will not transition, it will remain at 0. Or we can pretend that we're trying to reset it. And therefore, if we apply a 1 over here, it will reset, but of course it will try to reset from an already 0 state. So there's going to be no transition really. However, the reset signal for B can be anything you want. It can be 0 or it can be 1. That's what this whole thing leads to. And so this will be a don't care for this signal, and we can use it later on for optimizing the circuits that we're going to produce. In this particular state, 001, because it is a state that is not used and will never appear, the next states can be anything you want. Therefore, all of the entries for all the controls are going to be don't cares. If we take another entry where, say, the flip-flop A over here is 1 and it remains at 1, so there is no transitioning. So what should the controls be for flip-flop A? Well, the reset for sure has to stay at 0. Okay, you cannot activate the reset because you don't want to reset it. However, the set can be anything you want. If it is at 0, so controls 0 and 0 would cause the flip-flop to do nothing, and therefore it will still remain in the state that it was, which is 1. Or you can pretend that you're trying to set it. Of course, trying to set it from a state of 1 is really not going to change anything because you will be setting it from state of 1, so it will just remain at 1. But the signal SA will be a don't care, because it can be anything you want. Either way it will work, as long as the reset is held at 0. Let's take this case, the flip-flop C. Flip-flop C over here, in the very last state, it is at 1 and it needs to go to 0. So obviously we need to reset it. And that entry is shown over here for the flip-flop C. The set is at 0 and the reset is at 1. So it is resetting. That is basically it. Practically, we're looking at the activations for the various flip-flops, and we fill the table accordingly. So in this particular case, looking at the flip-flop RS, looking at the transitions that you desire, you fill the appropriate controls in this table. Again, you take any transition you can see over here. So for example, this one is a 0 to 0. The flip-flop is an RS flip-flop. So what controls do I need to apply to flip-flop C? Going back here, I see that for an RS flip-flop, for a 0 to 0 transition, I need these controls. Therefore, those controls are going to be over here. If you're looking at a 0 to 1 transition, 0 to 1, again, flip-flop C goes from 0 to 1 over here. A 0 to 1 transition for a flip-flop that is of type RS requires controls 1 and 0. So if you look at all the transitions where you have a transition from 1 to 0, the flip-flop controls are exactly these. See, 1 to 0, the flip-flop controls are exactly what we had on the table. So for every transition, you consult this table, you select the appropriate flip-flop that it is that you're using, and you can copy the controls from here onto the table. And that makes the augmented transition table, which shows not only the current states and the next states, but it also shows the required controls that will make the flip-flops dance in the way that you want them to dance in order to achieve this transition. So the next thing to do is, of course, to obtain the Boolean functions for those controls and optimize them. So this is, in fact, the truth table for all these functions. All of these signals will be simple Boolean functions. Okay, each one of them will be a Boolean function with inputs that being the current state, A, B, and C. So the outputs, the current outputs of the flip-flops are going to be the inputs to these Boolean functions that are going to produce these signals. Just as shown over here. So the outputs of the flip-flops become inputs to the Boolean functions that are going to produce the control signals for the flip-flops. And the truth table for those functions is going to be exactly this. So from here on, you implement each one of these functions in the way that combinational circuits are designed. This one shows independent implementations for each function using Carnot maps to simplify them, or you can use PLAs, or you can use memories to burn the truth table in there and have all the functions performed by that memory, or any other of the methods used to build combinational circuits. All right, so with these and getting the reduced expressions, you see the reduced expressions are very simple for the flip-flop A, and they're still simple enough for flip-flop B. They're a little bit more complicated for flip-flop C. But with these equations that we have produced, the implementation of the system is this one. So the combinational circuit that we were showing earlier is basically consisting of these gates. So this combinational circuit right here, the controls, will consist of these gates. Now, in order to keep this diagram not very cluttered, the way that the signals are designated, as you see, we have over here A and A prime complement, C, and so on. All of these are coming from here. So essentially, this signal would have to be wired right here, and this signal would have to be wired right here, and so on. But that would make the design a little bit complicated to look at, and so it is specified like this. But it's a complete specification. Now, the end gates that are feeding the R and S signals are also using a external signal, a control signal called the pulse. This will be a synchronization signal. Only when this signal appears, a transition will be possible. What this does is it makes certain that the circuit that we have built will only make its transitions only when this signal comes in. And usually this is a pulse signal coming from a device that we call a clock that generates a waveform that consists of pulses. And so all of these gates are going to open when the pulse is active, and the signals will activate the flip-flops to do their transitions. So all the transitions are going to happen in sync with this signal. Next, let's do this with JK flip-flops. The procedure is similar no matter what kind of flip-flops you're using, and in this particular case we're going to do it with JK flip-flops. The steps are exactly the same as before. What we're going to do is we're going to fill the table with the control signals required for JK controls. So again, we're going to look at the various transitions. So flip-flop A, in this particular case, has a transition from a 0 to 1. Looking at the transition from 0 to 1 for a JK flip-flop, we see that the controls that we need are going to be 1 and don't care for the K. So this is what is entered right here on the table, 1 and don't care for JA and KA, the controls for flip-flop A. The controls for flip-flop C, going from 0 to 0. We have a transition from 0 to 0, no transition in other words, and a flip-flop JK, therefore we need these controls, 0 and X. So the controls for flip-flop flip-flop C, the controls for flip-flop C are going to be 0 and X, since flip-flop C is going from 0 to 0. And similarly for the B, 0 and X, because it's going from 0 to 0. Again, in the case of a state that is never going to appear, everything is going to be don't cares. For a transition from 1 to 0, flip-flop A in the very last entry, 1 to 0, we need controls X and 1 for J and K. Therefore, JA and KA are set over here to X and 1. A transition from 0 to 1, so flip-flop C in this particular case, a transition from 0 to 1 requires controls 1 and X, so the controls JC and KC for the flip-flop C are set to 1 and X, because a transition 0 to 1 for a JK flip-flop is 1 and X. A transition from 1 to 1, well, no transition really, but remaining at 1 requires controls X and 0. Therefore, flip-flop B over here that remains at 1 in this particular case requires controls X and 0. So with this logic, we fill this table, and now we have the truth table for all the control functions, and then we go and implement all of these control functions as Boolean functions using any method that we like, whether that is gates or using multiplexers, using memories, using PLAs, using whatever. In this particular case, we're doing it with gates and using Carnot maps for reducing all those functions. And you can see that the Carnot maps have been filled with the entries from this truth table. The don't care conditions will help us minimize the function even more than we would without them. What these tables are shown are only the zeros and the x's. Everything that is blank is supposed to be 0. And given these Carnot maps, your reduced expressions would be these ones. And with these expressions, the circuit that we obtain is this. Now, these are JK flip-flops. The JK flip-flops have a clock input, and they only change their state when the clock input activates them to change state. So what these gates do, and these connections do, see for example the JA was just B naught, and so it's just a straight wire here. These are gates. So given the current state, the flip-flops receive their control signals, but the control signals are not going to cause a transition until this pulse comes in, this controlling pulse. Only when this comes in, the flip-flops will be able to transition. For that, you can refer to the master-slave flip-flop and the control input that it has in order to allow it to only make transitions at specified points of time, a rising edge of a signal, of a control signal, or the falling edge of a control signal, depending on how it is wired. So this is the implementation of the same circuit using JK flip-flops. Now I'm going to take the opportunity to show you a simulator, and for that purpose I'm going to use the Simuade, which is a simulator that came with Roth's book. So here is the design already made. Let me explain a couple of parts. These JK flip-flops that came with the library of the Simuade have set and reset inputs to bring the flip-flops to a certain state. If you wanted to reset the whole system, for example, you can reset it by activating these inputs. Now, these inputs have this little circle here, which means that they're active low. That means in order to activate them, you have to ground them. So in order to get the simulation going, we need these inputs inactive. The set and reset must be inactive. For that reason, we need to connect them to 5 volts, the power. So this is a power part, and this power voltage is connected to the reset over here, and then in this line connects it to the set over here, and then these two lines connected to these other inputs, the remaining inputs. So all of these inputs now are inactive since they're connected to power, and since normally they would be active low. So we're ready to start with a simulation. The system is at the state 000 as the probes show over here. This is flip-flop A, this is B, and this is C. So at state 000, the next state should be 100 according to the original flowchart, and also according to the state transition table. It shows here that after 000 we should find ourselves to 100. So if I step the simulation, there we go. The system found itself to 100. Again, if I step the simulation again, it finds itself to state 111. And indeed, that is what is expected. So from state 100, the next state is going to be 111. The next state after 111 should be 010. So if I step it again, there we go, 010. And so we can verify that the system is working properly by running the simulator and getting the entire state transition diagram to be verified in this way. Next, we're going to do the exact same thing by using D flip-flops. And again, we need to fill the table with the control signals. In this case, the control signals are going to be simply DA, DB, and DC. The D flip-flop has only one control signal, control input. It still has a synchronization pulse signal called a clock signal, because the input is going to be latched to the output, or in other words, the input will be copied to the output and will remain stable only when that control signal appears. Then the flip-flop is going to read its D input, and its output will become whatever that D input is. But that's going to happen only when the control pulse arrives. But the concern that we have here is, what should these D inputs be? We have three flip-flops, therefore we have inputs DA, DB, and DC. Again, we're looking at possible transitions. And if you look at A going from 0 to 1, you can consult this table for transition 0 to 1. What happens with a delay flip-flop? See, the delay flip-flop says that your control input has to be 1 in order to achieve a transition from 0 to 1. As a matter of fact, if you look at the whole column for D, it's exactly the same as the next state. And again, it's obvious why that should be, because the D is going to be the next state. So if you want this to be the next state, then the D better be exactly that. So for the case of the D flip-flops, it's really a no-brainer. The controls for DA should be exactly what the next state of A should be. So this column is copied over here exactly, where the dashes have become don't cares, because the dashes mean a condition that's never going to appear. Therefore, the signal can be anything you want at that point. So that is what we're doing here. We're copying this column over here. And similarly, we're copying column B to the control DB, and column C to the control DC. And now we have the truth table for DA, DB, and DC. This truth table specifies what the functions DA, DB, and DC should be when their inputs are A, B, C. Okay, so these are the inputs, and this is what we want produced by the control circuit. And this is the truth table for them. Again, doing Carnot maps or any other method that you like, but in this case we're using Carnot maps. We obtain the control equations. This is DA, this is DA, this is DB, and this is DC. And the implementation is this one. Notice that, as I said earlier, that the delay flip-flops, they have a control input. It is a pulse signal that comes in. It is usually specified as the clock input. And when this input activates the flip-flops, then whatever is at the input will be latched to the output. And all of this circuit ensures that the inputs to the flip-flop, which are going to be the next state that the flip-flops are going to latch to, is the appropriate one based on what the current state is. So this is the current state. The current state will produce control signals over here. So when the clock pulse comes, these control signals will make the flip-flops do what needs to be done in order for them to go to the next state appropriately. And that is how you do it with delay flip-flops. Now, trigger flip-flops. Trigger flip-flops, the same thing again. All right. If we are having controls TA, TB, and TC, we can consult the activation table for the flip-flops again to see what we would need for a transition, say from 0 to 1. For a transition from 0 to 1, for a trigger flip-flop, you need a 1. As a matter of fact, remember that the trigger flip-flop requires a trigger only whenever you have a transition. So you have ones here when you have these transitions. When you don't have a transition, then you do not require an input. So the inputs are 0 in that case. So trigger flip-flop. Trigger makes it toggle. That's basically what you need to remember. So you can consult this table, but you really don't need to. It's a no-brainer to see that you need the trigger only whenever you have a transition. So here you have a transition from 0 to 1, you have a 1. Over here you don't have a transition, 0 to 0, 0 to 0. Therefore, you don't have a transition, you don't need to do anything. From here, 1 to 1, you don't have a transition, you don't need to do anything. Here you have a transition from 1 to 0, therefore you need a trigger. So comparing this column to this column, whenever you have a transition, you put a 1 over here. Whenever you do not have a transition, you put a 0 over here. In the cases of codes that are never going to appear, or states that are never going to appear, you have don't cares. And that's it. This is the trigger for flip-flop A. Similarly, this is the trigger for flip-flop B. And similarly, this is the trigger for flip-flop C. So we have now the truth table for the function TA, TB, and TC when on inputs ABC. So now we're going to proceed to design the circuit. Now I don't have that circuit completed, and I'm going to complete it and show you exactly all the steps for doing it. So what I'm going to do now is I'm going to switch to the simulator, Simuade, or now I don't have this circuit completed, and I'm going to complete it now, and I'll do so just to show you some other tools that you can use to do this. For this purpose, I'm going to use Logic Aid, which is a tool that comes with Roth's book. And I'm going to simply design these using Carnot maps to reduce the expressions. So here is the Logic Aid, and what I'm going to do is I'm going to say that I need a truth table of 3 variables, 3 functions, and I can enter names. So this is going to be A, this is going to be B, and this is going to be C, which are going to be the outputs of the flip-flops, because those are going to be inputs to the T functions. And the functions that I'm looking for is the TA, the TB, and the TC. Okay, now I need to enter the truth table here. For 0, 0, 0, A, B, and C, what should be the TA, TB, and TC? So if we look at the truth table that we have, for 0, 0, 0, the TA, TB, and TC should be 1, 0, 0. So 1, 0, 0. Next, for 0, 0, 1, I get X's. X, X, and X. For 0, 1, 0, I get 0, 0, 1. 0, 0, 1. For 0, 1, 1, I get 0, 1, 1 again. So 0, 1, 1. And then for 1, 0, 0, I get 0, 1, 1 again. For 1, 0, 1, I get X's, and so do I get for the next line. So I put X, XX, and XXX. And for the last one, I get 101. 101. Okay. So this is my truth table. Now, what do I want to do with this table? I can simplify. I want sum of products form, and I'll just keep the defaults over here and say okay. Okay, it doesn't like my axis. I think they need to be dashes. So let's put them as dashes. There you go. And then say simplification. Okay. And there you go. So the simplified functions for TA, TB, and TC are shown over here. So I can take these and I can go and build the circuit now. So now, given these equations, I'm going to design the circuit, and I'm going to do it as follows. I have 3 flip-flops here, supposed to be trigger flip-flops, and the control for A is going to be A naught and B naught, or A and C. So I built the A naught and B naught right here, and then I need to build A and C. So I have built here the A and C, and now I need to OR these together. I need to OR these together in order to provide the signal for the flip-flop A. So this completes the input for flip-flop A according to this equation. I'm going to build TC because it's easy. Next. So here I have B or A, and the last one is A naught C or A B naught. And here I have the last of it, with this one doing the C and A naught signal and A naught signal, and this one doing the B naught signal and the A signal all together into B. And this is the completed design.